collisions. And remember, elastic collisions are where things bounce off each other and kinetic energy is conserved. So your homework question for tonight is this. Mr. Munson and Mr. Pearson are in the Calhoun room playing pool. On Mr. Pearson's recent shot, the cue ball was moving east at 0.82 meters per second when it struck the slower 5 ball, moving in the same direction at 0.24 meters per second. The 5 ball immediately speeds up to 0.52 meters per second. Determine the post-collision speed of the cue ball. For this problem, it might be really, really helpful to draw a picture. So momentum is always conserved in every collision ever in an isolated system. It does not matter if it is elastic or inelastic, but kinetic energy is only conserved in an elastic collision. So when we have an elastic collision, like the pool balls bouncing off each other in the homework question, kinetic energy is always conserved. So the two rules of elastic collisions is that momentum is conserved. The total momentum before the collision, meaning the added momentum of each object, equals the total momentum after the collision. And total kinetic energy is conserved. The total kinetic energy before the collision equals total kinetic energy after the collision. And when we're talking about total momentum and total kinetic energy, for both of those, you need to take the sum of the kinetic energy or momentum of each object. So you need to add it together. So we have two equations that apply to elastic collisions. The first one we already know, the conservation of momentum. Momentum before equals momentum after. Elastic collisions are ones in which the objects do not stick together. They stay two separate objects. So we have the momentum of the first object, m1v1, plus momentum of the second object, m2v2, and that's before the collision. And that's equal to momentum after the collision, m1v1 prime plus m2v2 prime. So they stay two separate objects. But the second equation that applies to elastic collisions is the conservation of total kinetic energy. Hopefully you all remember the equation for kinetic energy. It is 1/2 mv squared. So if we work our way through this line by line, the conservation of total kinetic energy tells us the total kinetic energy before a collision equals total kinetic energy after. In order to solve for the total kinetic energy, we need to add the individual kinetic energies of each object. So here we have two objects. So we have the kinetic energy of object 1 before the collision, and we add it to the kinetic energy of object 2 before the collision. And that has to be equal to the kinetic energy of object 1 after the collision plus the kinetic energy of object 2 after the collision. Remember, we're using our primes here to mean final. And if we expand this one step farther, we can plug in our equation for kinetic energy. So the kinetic energy of object 1 initially is 1/2 m1v1 squared. Its mass times its initial velocity squared. Same for initial kinetic energy for object 2, except now you have its mass and its velocity before the collision. And then we can plug in the equation for our final kinetic energies. 1/2 m1v1 prime squared. I know it looks scary, but it's really not that bad. All this means is the final kinetic energy of object 1 is 1/2 times its mass times its final velocity squared. That's all it means. And we add that to the final kinetic energy of object 2. I know it looks long and complicated, but it's really just, it comes down to plugging and chugging. All you have to do is be able to look at a problem and say, okay, these things are bouncing off each other. I bet it's an elastic collision. And because it's elastic, that means kinetic energy before equals kinetic energy after. And then you can follow each of these steps down for your problem solving. So usually, what we'll have you do is find the velocity of an object after a collision, and then ask you to show us if it's elastic or inelastic. If it's elastic, initial kinetic energy should be equal to final kinetic energy. If it's inelastic, those two numbers will not be the same. So let's do an example together. A 1 kilogram ball sliding to the right on a frictionless surface at 10 meters per second makes an elastic head-on collision with a 2 kilogram ball moving at 5 meters per second to the left. After the collision, the 1 kilogram ball is moving to the left at 10 meters per second. Using the conservation of momentum, what is the velocity of the second ball? Is this an elastic collision? Why or why not? So the first thing that I'm going to do is draw a picture, because there are a lot of words here. So we have a 1 kilogram ball. Well, actually, I'm going to draw it a little bigger. We have a 1 kilogram ball sliding to the right at 10 meters per second. And it makes an elastic head-on collision with a 2 kilogram ball traveling at 5 meters per second to the left. Now, before we go any farther, we have something traveling to the right and we have something traveling to the left. And we need to be able to signify direction in our equations. So we need to assign positive and negative to these directions. You can do it any way that you want, but I typically assign to the right as moving in the positive direction. So in that case, the 1 kilogram ball has a velocity of 10 meters per second, and the 2 kilogram ball has a velocity of negative 5 meters per second, because it is moving in the negative direction. So now that we have our picture, they are going to collide. 1 and 2. And after the collision, our 1 kilogram ball is moving in the negative direction now, to the left, at 10. Sorry, not 5. So it has a velocity of negative 10. And our 2 kilogram ball, we don't know. It might be moving this way, it might be moving this way, it might not be moving at all. That is what we're trying to find out. So now let's go through and list everything that we know from this problem. I'm just going to get a new sheet of paper here. So everything that we are given in this problem, well, we have the mass of the first ball is 1 kilogram. The mass of the second ball is 2 kilograms. The initial velocity of the first ball is 10 meters per second. And the initial velocity of the second ball is negative, don't forget the negative, 5 meters per second. We also know that the final velocity of the first ball, or v1 prime, is now negative 10 meters per second. And what we are trying to figure out, at least for the first part, is what is the velocity of the second ball? So we want to find v2 prime. Now, in order to solve this problem, we need an equation. And looking at everything that we are given, hopefully it's jumping into your head. Momentum is always conserved in collisions, so we need to use the conservation of momentum equation. You would be correct. So we have m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And I ran out of space. There we go. So now all we have to do is plug our numbers in and solve. So we have 1 times 10 plus 2 times negative 5 equals 1 times negative 10 plus 2 times v2 prime. 10 plus negative 10 equals negative 10 plus 2 times v2 prime. 0. 10 plus negative 10 is equal to negative 10 plus 2 v2 prime. Subtract 10 from both sides, we get 10 is equal to 2 times v2 prime. And when we divide both sides by 2 to solve for v2 prime, we find that the final velocity of the second ball is 5 meters per second. But that's only the first part of the question. We also want to know, is this an elastic collision? Now, here is where the definition becomes important. So what makes an elastic collision different from an inelastic collision? It is the fact that kinetic energy is always conserved in an elastic collision. So we want to know, is kinetic energy conserved or not? If it is, this is elastic. If it's not, it is inelastic. So what we need to do is solve for the kinetic energy in the beginning and the kinetic energy after and see if they are equal. So we are going to use these crazy looking equations, the ones that look scary but they're not that bad. So we know that kinetic energy before should be equal to kinetic energy after if this is an elastic collision. If you set these two things equal and you get two different numbers, say 7 is equal to 10, you know that this is an inelastic collision because 7 is not equal to 10. They are two different numbers. And therefore, the initial kinetic energy can't be equal to final kinetic energy. But if you set these two things equal to each other and you find that you get the same answer on both sides, 7 equals 7, this is an elastic collision. So we have 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Kinetic energy of the first ball in the beginning plus kinetic energy of the second ball in the beginning is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. So that has to be equal to the final kinetic energy of ball 1 plus the final kinetic energy of ball 2. And now we're plugging in numbers. So we have 1/2 of 1 times 10 squared plus 1/2 of 2 times -5 squared equals 1/2 times 1 times -10 squared plus 1/2 times 2 times 5 squared. So when you do this all out, you have 10 squared is 100. And when you divide 100 by 2, you get 50. So we have 50 plus -5 squared is positive 25. You have -5 times -5, and two negatives multiplied together makes a positive. So it's positive 25. 25 times 2 is 50. Divided by 2 is 25 again. So this is 25. Ooh, should make that red. And that is equal to -10 squared is 100, positive 100. Divide that by 2, you get 50. Plus, hopefully you're starting to see the pattern here. 5 squared is 25, times 2 is 50, divided by 2 is 25 again, so we have 25. So we get 50 plus 25 equals 50 plus 25. So the total answer is 75 is equal to 75. And remember, we are solving for kinetic energy. We need some units here. The energy units that we use are joules. So 75 joules equals 75 joules. Okay, so basically what we have now proven is that the initial kinetic energy equals final kinetic energy. That makes this an elastic collision. So is this an elastic collision? Yes. You should be familiar with this. It's a long problem to do, but it's not that difficult. Find or use conservation of momentum to find any unknowns, and then check and see if your initial kinetic energy of the system equals final kinetic energy of the system. So go ahead back to our first problem about Mr. Pearson and Mr. Munson playing some pool, and see if you can determine the speed of the cue ball after the collision.